Pluto. The frozen world that refused to stay dead for decades, Pluto was treated as a distant and insignificant object at the edge of the solar system. It was tiny, incredibly cold, and so far away that scientists could barely make out anything about its surface. When Pluto was discovered, people celebrated it as the ninth planet. It appeared in textbooks, classrooms, and maps of the solar system. But later, its planetary status was changed, and Pluto became known more as a mysterious dwarf planet than a true member of the planetary family. For a long time, scientists assumed there was not much happening there. Then spacecraft and powerful telescopes began changing that picture. The New Horizons mission gave humanity its first close look at Pluto. Instead of revealing a simple frozen rock, it discovered towering mountains, enormous plains of frozen nitrogen, strange surface patterns, and a thin atmospheric haze. Pluto was far more complicated than anyone expected. And later observations with the James Webb Space Telescope began revealing even more about its atmosphere and chemistry. What scientists found suggested that Pluto is not simply a frozen object drifting through darkness. It is a world with an active atmosphere, complex chemistry, changing surface processes, and possibly even an ocean hidden beneath its icy exterior. To understand why Pluto is so strange, we have to go back to its discovery. The astronomer Clyde Tombaugh discovered Pluto while searching through photographic plates for a faint object moving against the background stars. The discovery was remarkable because Pluto was incredibly difficult to see. For decades afterward, Pluto remained almost completely mysterious. Its enormous distance from the Sun made detailed observations extremely difficult. Its small size meant that even powerful telescopes could not clearly resolve its surface. So scientists had to make educated guesses. Pluto was imagined as a frozen, inactive body sitting at the edge of the solar system. But that idea began to collapse when New Horizons reached Pluto. After years of traveling through space, the spacecraft finally passed the dwarf planet and sent back images that transformed our understanding of it. One of the most recognizable discoveries was the enormous bright region shaped somewhat like a heart. Nearby were mountains made largely of water ice. Since Pluto is so cold, that water ice behaves more like solid rock than the familiar ice we see on Earth. There were also vast regions covered with nitrogen ice. Some of these frozen materials appear capable of moving slowly across Pluto's surface, creating processes that resemble glaciers on Earth. A thin bluish haze was also discovered high above the surface. These observations made one thing clear. Pluto was not a simple frozen pebble. It had geology. It had an atmosphere. And its surface had been changing. But New Horizons only had a short opportunity to observe Pluto during its rapid flyby. That left scientists with an obvious question. What else could be happening there that we had not yet seen? This is where the James Webb Space Telescope became important. Webb cannot travel to Pluto, but it can study the light coming from the distant world. By examining that light, scientists can learn about molecules in Pluto's atmosphere, the behavior of its surface materials, and the chemistry taking place far beyond Neptune. One of the most fascinating parts of Pluto is its atmosphere. Compared with Earth's atmosphere, it is extremely thin. It is dominated by nitrogen, with smaller amounts of methane and carbon monoxide. Despite being so weak, this atmosphere is not completely static. Pluto's surface is surrounded by layers of haze produced through chemical reactions high above the ground. Sunlight reaches Pluto even though it is incredibly weak there. That faint energy can still interact with methane molecules in the atmosphere. The molecules break apart and react with one another, eventually producing more complicated hydrocarbons and other organic compounds. These particles can become part of Pluto's famous reddish-brown haze. Eventually, some of this material settles toward the surface. In a sense, Pluto is constantly producing its own strange chemical snowfall. But the haze does something even more interesting. Instead of simply trapping heat, the haze can help Pluto lose energy. The particles absorb incoming radiation and then release energy back into space as infrared radiation. That means Pluto's atmospheric haze can contribute to cooling the atmosphere. A world that is already unimaginably cold can actually lose even more heat through this process. The temperatures on Pluto are far beyond anything humans experience naturally on Earth. Nitrogen can exist there as solid frost. Methane can become frozen onto the surface. Carbon monoxide can also form frozen deposits. Materials that are gases under Earth's normal conditions can become part of Pluto's landscape. And while all of this is happening, chemical reactions continue in the thin atmosphere. Compounds such as ethane, acetylene, and other complex hydrocarbons can form from simpler molecules. Over enormous periods of time, these materials can settle onto Pluto's surface. Some of them contribute to the dark and reddish colors seen across parts of the dwarf planet. The mystery beneath Pluto's frozen surface, but the deeper scientists look into Pluto, the more complicated the picture becomes. The possibility of an underground ocean is especially important because Pluto is located in one of the coldest and darkest regions of the solar system. The sunlight reaching it is incredibly weak, yet the interior may still have enough energy to keep water from freezing completely. That energy could come from radioactive elements inside the rocky core. Over enormous periods of time, radioactive materials release heat. On a small world like Pluto, that heat might not be enough to create anything resembling Earth's volcanic environment, but it could potentially maintain pockets or layers of liquid beneath the surface. If Pluto really does contain an underground ocean, then its frozen exterior would be hiding a completely different environment underneath. The surface could be covered in nitrogen and methane ice while liquid water remains trapped far below. That creates an extraordinary contrast. Above the crust is an environment where gases freeze solid. Below it could be an environment containing liquid water. And between those two extremes is a thick layer of frozen material that has survived for billions of years. This possibility also raises another question. Could Pluto's surface features be connected to what is happening deep inside? The unusual mountains and possible cryovolcanic structures suggest that material from the interior may once have moved upward through cracks and weaknesses in the crust. If that happened, Pluto's interior could have remained active for much longer than scientists originally expected. The strange thing is that Pluto does not need strong sunlight to remain interesting. Its activity may be driven by internal processes rather than energy from the sun. That is important because it changes the way scientists search for potentially interesting environments across the solar system. For a long time, scientists naturally focused on places receiving enough sunlight to support familiar planetary processes. But Pluto demonstrates that distance from the sun does not automatically mean complete inactivity. A world can be extremely cold on the outside and still have important processes happening underneath. This idea becomes even more interesting when we consider Pluto's unusual orbit. Pluto takes a very long time to complete one trip around the Sun. As it travels along its enormous orbit, its distance from the Sun changes considerably. That means Pluto's environment is not permanently fixed. When it moves closer to the Sun, its surface receives more energy. Some frozen materials can begin to change phase. Gases that were deposited onto the surface can return to the atmosphere. As Pluto travels farther away again, the temperature drops and some of those gases can freeze back onto the ground. The atmosphere can therefore expand and collapse over long periods. Pluto effectively experiences a planetary cycle that unfolds across an enormous span of time. A person could live an entire lifetime without witnessing more than a tiny fraction of this transformation. That makes Pluto difficult to understand through ordinary human timescales. Its world changes slowly, but the changes can become enormous when given enough time. The same is true of its relationship with Charon. The material moving between the two worlds does not create a dramatic event that could be watched from Earth. Instead, tiny quantities of gas and frozen material accumulate over immense periods. Radiation gradually changes molecules. Surface deposits slowly grow. Colors slowly develop. What looks like an ordinary dark patch may actually represent a chemical history extending back for millions or billions of years. This is one of the reasons Pluto's surface is so valuable to scientists. It acts almost like an archive. Different regions preserve evidence of different processes. Some areas appear relatively young. Others are extremely ancient. Some are dominated by bright frozen materials, while others are darkened by complex organic compounds. Together, these landscapes tell the story of a world that has been changing for an extraordinary length of time. And there is another strange feature. Pluto's surface contains enormous differences in brightness and color. The famous bright region contrasts sharply with darker terrain around it. These differences are not simply artistic patterns. They are connected to the different materials covering the surface and the way sunlight and radiation interact with them. The darker areas contain more of the complex organic material created through atmospheric chemistry. The brighter regions can contain large deposits of frozen nitrogen and other volatile substances. These materials can move across the surface as Pluto's environment changes. So even the colors of Pluto can reveal something about its history. The surface is essentially recording the chemistry of its atmosphere and the changing conditions of its orbit. That makes Pluto more like a dynamic laboratory than a frozen stone. And the chemistry gets even more interesting when radiation enters the picture. Space is filled with energetic particles. They constantly interact with exposed surfaces throughout the solar system. On Pluto, these particles can penetrate frozen materials and alter their molecular